record. Okay, to our warm-up, first of all. The first one, again, just kind of a common thing that we see, things like ratios and whatever, and it's talking about the ratio, which means it's not necessarily that the radius was 9 and the radius was 16, but they were some multiples of that, and when we simplified down that fraction, we got 9 over 16. But it could have been multiplied by something, right, that got simplified out of there. Like maybe they had both been multiplied by 2. It could have been like 18 over 32. There's some multiple of 9 and 16, so it could have been some random number multiplying top and bottom, which is not important, but understand that it would simplify down to that. But if I multiply by the same thing, top and bottom, it would always simplify down to 9 over 16. So knowing the formula for the circumference is just multiplying the radius by 2 and by pi, right? It's 2 pi r is your circumference formula. Okay, well, if I take this radius and multiply by 2 and by pi, and multiply this radius by 2 and by pi to get the circumference over the circumference, well, wouldn't all of that stuff still simplify out of there and get you the same ratio of 9 over 16? Okay, so it's got the same ratio of their circumferences is also 9 over 16. Moving on to the second one, they're asking us to plug in x plus h in here and remembering how we deal with that. So if I plug in the x plus h where there was an x, right, we practiced evaluating our functions the other day, and I'm going to plug that in there, it ends up that I got a lot of variables, okay, and it gets a little ugly, but I have to write x plus h twice and FOIL first. Okay, well, when I do that, I get x squared, xh would be 2 xh's. And h times h is h squared. That would have been the FOIL part of it. And then I have to distribute a 2 through that. And then there's nothing else to do. There's no like terms to combine. It was option K. All right, today we are moving on to 1.3 day 2, which is the topic of symmetry. Our learning goals, we will be able to test for symmetry and know if our function, or I shouldn't say function, if our graph is symmetric with respect to the y-axis, with respect to the x-axis, or with respect to the origin. Symmetry means the same on both sides. So think if I were to fold our graph on that line, and I were to be able to see what when I folded it, that it would match exactly up with itself on that line. So for example, a symmetric around our y-axis means that whatever is happening to the left of the y-axis has to match, or if I were to fold it over here, it would match exactly with what's happening on the right of that y-axis, okay? And so this is giving us the line that we're folding on to match up exactly with itself when we talk about symmetry with respect to something. All right, of what you are going to see on this page, and I'm going to zoom in just a little bit, I will tell you that the important part is that last column. Thank you, you too. You need to know how to test for the symmetry. Okay, so I'm going to zoom in a little bit so you can see this a little bit better. If we say that something has respect to the y-axis, you don't necessarily need what's written under here, but it is true that with respect to the y-axis, every point on our graph that is of the format x comma y, with respect to the y-axis means that you would also have a point with those same two numbers, but the y would, or the x would be negative. Negative x comma, same y value, folding over our y-axis. Now the test is the important part. Please make sure you have that in your notes well so that you have some place to reference this. When testing for, and this is kind of my little trick here, opposite letter. If I'm testing for symmetry about the y-axis, I would go replace the other letter. Replace x with negative x. If I can then clean up the equation and I get back to the exact same thing I started with, then I have confirmed that it has symmetry about the y-axis. For each of those test column ones, I have a very basic example to show us of that happening. So given the equation here, here's my tiny little example, y equals x squared. To test it for symmetry about the y-axis, I take out the x and I plug in a negative x. I clean it up, and I need to match. This is my original, and I need to match the original when I do that. So I would plug in negative x. Okay, well, the cleaning up process is pretty quick on this. Negative x squared is the same thing as positive x squared, right? Because it's raised to an even exponent. And so this would clean up to y equals x squared. And notice that is the same as the original, which is what we're looking for. If it matches the original exactly, it has symmetry about the y-axis. Questions? X-axis symmetry, very similar, but flip all the letters, okay? In order for something to have x-axis symmetry, every point that is on your graph, and this is really small, so I'm going to make it bigger, every point on your graph that you could call some x comma y, you would also have a second point on that graph that would have the same x value, but the opposite y. So down here, you would see this is the point x comma negative y. It's flipping it over your x-axis. Okay, so if we folded it over our x-axis, it would match up exactly with itself. Just like I talked about for testing for our y-axis symmetry, we replaced the other letter. You're going to do the same thing for x-axis symmetry. You're going to replace the other letter. So if I am testing for x-axis symmetry, I replace y with negative y, always replacing the other letter. My very basic example for you is the equation x equals y to the fourth. If I were to test this for x-axis symmetry, I would replace y with negative y wherever there was a y in our equation. I would have to remember my algebra rules, and my algebra rules say that if I ever raise something to an even exponent, it always turns out positive regardless of what I plugged in there, right? So negative y to the fourth is actually going to simplify down to just y to the fourth. So then I could clean up this as x equals y to the fourth, and then I see that it is the exact same as the original. I have now just shown by my algebra that it has x-axis symmetry. Simple as that as far as the showing part of it. Okay, now, a little more important on this next one, because there is one more step, and eventually when you get assessed over this, the verification via what I'm showing right there, it doesn't take a lot, right? But knowing how to do it is what we're asking. Do you know how to verify these or to test for that symmetry? The last type of symmetry is what's called symmetry about your origin. Now, the origin is not a line that I can like fold over, okay? So what you want to think about is spinning. It's a point, isn't it? And so if I were to spin my graph around the origin, half a circle, 180 degrees, it would match exactly up with itself. I can kind of tricky do that. If you look at how this picture looks right now, if I were to turn it upside down or spin it 180 degrees, you would notice that it looks like what it looked like before I turned it upside down. Okay, so being able to spin a graph 180 degrees and get the exact same picture that we started with means it has symmetry about the origin. On that, each of your points completely switches signs. So any point that I started with originally, any x comma y that I start with, when it has symmetry about the origin, has the exact opposite pair. So we would also have, if this was a point on my graph, I would also have negative x comma negative y. There is no like opposite letter to plug in. You know, like how I said, testing for the y-axis, plug in the other letter. Testing for x-axis, plug in the other letter. Well, there's no other letter for origin. That's your indication to just plug in both. Okay? You have to plug in x for negative x, y for negative y, and if you can clean that up and get back to the original, it has symmetry about the origin. My very basic example to you, and I think this is one of our better ones for showing the clean it up, is this equation. Y equals x cubed, okay? So if I go plug in negative y for y and negative x for x, okay? And I clean it up. First of all, using my exponent rules, negative x cubed is still going to be negative x cubed, right? Remind you of your algebra rules here. Anything raised to an odd exponent stays whatever sign it was. It will not always come out positive. It will stay. So this is going to stay negative x cubed, which is not what our original looked like. But does anyone see a little algebra trick I could maybe do to get it to look like the original? Divide by perfect. Divide by -1. I can divide both sides by the same thing without changing the fact that it's equal, right? So if I do a little algebra trick here, I have the exact opposite signs I want. Divide by -1. That makes the y positive, that makes the x cubed positive, and that makes it match our original now. And if I can move things around, use some algebra manipulation here and get it to match the original, it has symmetry about the origin. Questions on that? One of the things we're going to look at is just testing for those symmetries without maybe even looking at what the picture looks like to give us a hint, okay? But we'll also consider graphs as we start getting into this a little bit further. So like on this first one, it says determine whether the graph of y equals, I'm sorry, that's an x. X equals y squared minus 1 is symmetric with respect to the y-axis, the x-axis, the origin. We just try out those different tests real quick. And if you're really good at your algebra, I know it looks like a lot, but it's really pretty quick. Okay, so let's remind ourselves of what those tests were. We're just going to test for all three and look at what the results are. Here's our original equation, and that's what we're trying to match on each of these. So if we're testing for y-axis symmetry, remember that means plug in negative x, right? If I can plug in negative x and get back to the original, y-axis symmetry. Oops. So plug in negative x. So I'm looking at negative x equals y squared minus 1. Is there anything I can do to this to get it to match the original exactly? I mean, if I divide by -1, it'll fix the fact that that's negative, but then these wouldn't match, would they? So there's nothing I can do. So it is not symmetric around the y-axis. Okay? X-axis, we plug in negative y, the other letter, always the other letter. And then we try cleaning it up and matching the original. Well, initially I see that the negative y squared could be written as positive y squared. Does this match our original? Yes. So that tells me that it has, let's see, has x-axis symmetry. That matches the original exactly. And our last one, we plug in both, right? So I'm going to plug in a negative x. I'm going to plug in a negative y. See if I can clean it up. Okay, well, the negative y is going to turn out positive. And then we're running into that same issue that we had over here, aren't we? And I can't get rid of that negative in front of the x without altering the other side that's already matching correctly. So it only has one symmetry, and that is about the x-axis. With that being said, it can be symmetrical around more than one of these, okay? So just because you find one does not automatically discredit the others. It is not, they are not mutually exclusive. You remember that phrase from Algebra 2? They are not mutually exclusive, okay? Anyone still need this page? All right. I do want to look at a picture of that equation. So here's the graph of what we were just working with. Here's the graph of x equals y squared minus 1. Okay, can you see how we said that it had x-axis symmetry? Do you see how that line right there runs exactly through the middle of our picture? Okay, and if I were to fold it over that line, it would match up exactly with itself. So just so you can kind of connect the visual to what we just found algebraically. All right, we're going to try this 2 more times here. My next equation that I want you to attempt this with is up there at the top. Y to the 5th equals x cubed. We're going to test it for y-axis, x-axis, and origin. Y to the 5th equals x cubed. Easiest way for me to remember how I test for these is that whole plug in the other letter thing, right? So if my test right now is for the y-axis symmetry, I would plug in negative x. If my test is for the x-axis symmetry, I plug in negative y. Always plug in the other letter. All right, so let's go ahead and try this out. First one, I'm going to plug in a negative x, and then we have to remember our exponent rules. Anything raised to an odd exponent just keeps whatever sign is there. So a negative x cubed is a negative x cubed. Can I do anything to fix that? I cannot. Okay, so it is not symmetric with respect to the y-axis. Let's check our x-axis. Plug in a negative y. Okay, and again, it's being raised to an odd exponent, so it will keep whatever sign it has. Can I fix that? No, I cannot. Okay, plug in both. Both are raised to an odd, so they keep whatever sign is there. Can I fix that? Yes. I would need to show one more step. Here, divide by negative 1, and I get back to the original. Okay? So it is symmetric with respect to the origin, meaning I can spin that circle, spin that in a circle around our origin, and it would match back up with itself. Let's connect this to the picture. Okay, so here is the picture of y to the 5th equals x cubed. Okay, can you see how if I were to flip that over our y-axis, this is not matching up with anything? If I were to flip that over the x-axis, it's not matching up with anything. But if I were to take this picture and spin it 180 degrees, doesn't it look like it did when we first flipped to this page, right? That's the same picture you were just looking at. So that's what the symmetry about the origin says, is if I can spin it 180 degrees, I get the same picture. Okay? All right, we got the last one. I told you we were going to do 3. X squared plus y squared equals 25. X squared plus y squared equals 25. Plug in the other letter. All right, let's look at our tests here. First one, I should have plugged in a negative x. It is being raised to an even exponent. All even exponents are going to result in a positive number, so I just drop that negative because it would turn out positive anyway. Does that match the original? Yes. So it has symmetry about the y-axis. Second one, we've got a oops, I wrote that wrong. And it would make a difference. There we go. I have a negative y being squared. Again, raised to an even exponent will always turn out positive, so that y will then be written as a positive y squared. Does that match the original? Yes, so this also has symmetry about our x-axis. And the last one, both of those raised to even exponents will both turn out positive, which means we get back again to our exact same original equation. So it also has symmetry about the origin. Now, we're going to take a quick trip back to Algebra 2. Did anyone recognize what shape you would get from that equation? It's a circle. It is. It's a circle centered at the origin because there's no pluses or minuses in there. So that's exactly what, and that makes sense then, right? If I were to flip that over my x or my y-axis, doesn't it match up with itself? Flip it over your x-axis, it matches up with itself. Spin a circle 180 degrees, it matches up with itself, right? So has all three of our symmetries here. Any questions for me about testing for symmetry? All right. We are going to skip over this because today we're going to do that online assignment. Now, grab your Chromebooks. If it is not working for you, which I looked and I believe there's only one person in here that was not showing up on my list, you have this book assignment. We will continue to have a backup book assignment until we get this thing like working perfectly, okay?